name on the presentation.
Because he doesn't want to make any claims.
You know, when my student does this, I will be very critical.
Yes.
Yes. You should feel yourself like that. Well, you are already very famous.
So where is Carl?
In the toilet.
Here is Carl. Where? Look behind the door. Look. Go and see behind there. Okay, so you can begin. So Boris, please, I already introduced
Okay.
you, so you can go on.
But you didn't introduce him to me.
Boris, this is Carl, this is Boris. And Jean-Pierre.
Okay, so first, many thanks to the organizers. Being a friend and colleague of Shiki, I know how much effort and time he put into this project. Well, I assume also other organizers contributed to organization. Well, second, I thank my collaborators on this work, Tampikos Kotas and his student Matthew Lee. And third, I think we should thank Hamas, Hezbollah, Jabhat al-Nusra, ISIS, all the terrorist organizations operating in our region for not firing rockets at us this time and letting us to proceed with our
Maybe we should
business.
thank the IDF for convincing them not to do that.
Actually, I think we should thank them because it gave us more time to prepare for this.
Exactly. Yes.
How do you look at this?
Okay, then.
Boris, I'm ready.
Oh, you already missed a good joke, but I... Okay, so this is the title of my talk, and recently we published a paper with a similar title. I'm saying similar and not identical because referee forced us to remove the PT-symmetry from title and abstract. He wrote that it's basically a sensible paper, quite straightforward, but that there is absolutely no reason for us to use this PT-symmetric, he called it PT-symmetric jargon, and make reference to PT-symmetric quantum mechanics. So we had to remove this PT-symmetry from title, but still we were able to keep one reference to Carl's review. And somewhere inside the paper, well hidden from the referee eye, we planted 1 or 2 sentences about PT symmetry. But well, here I'm still keeping PT symmetry. That's the title which was announced a year ago, so no need to change it here.
You're familiar with this stuff from the old Soviet Union, right? Where no one sees it.
Yes. No, all right. I don't know. I always develop some Parkinson symptoms when I keep this laser. Maybe I will use arrows. Okay, this is the outline of my talk. I will remind you what are these Landau-Lifshitz equations for magnetization. Then I'll discuss 2 coupled ferromagnetic layers in a PT symmetric configuration for 2 different geometries. At the end, I will propose 2 mechanisms for introducing gain into a ferromagnetic layer. So this is the Landau-Lifshitz equation for magnetization. Looks M is the magnetization, gamma gyromagnetic ratio looks pretty simple, but of course the point is that this effective magnetic field is not given. It is not known. It itself is a complicated function of magnetization and the external magnetic field. What we can control, not we, I mean experimentalists, can control is the external magnetic field. The magnetic field inside the ferromagnetic sample adjust itself to the external conditions. Well, even if there is no external magnetic field, we know that the sample is magnetized, and so it has some effective internal field. And generally, so it's a complicated nonlinear equation. In some geometries and under some conditions, things are getting much simpler. For instance, well, we know from electrodynamic course that if the sample has a shape of ellipsoid, and if its size not too large, because otherwise it can break into magnetic domain, so it's become even more complicated because this m and h will be function of position. But there are conditions when the relation is quite simple, that if the external field is uniform, then also the internal field, this effective field, is also uniform, but it differs in magnitude and direction generally from the external field. So this is the relation. N is called the magnetizing tensor. Okay, another point I want to make is that in the dynamics of magnetization, the size, the magnitude of the magnetic moment is conserved because, it's very difficult to change the magnitude of the magnetic moment. It is determined by the strongest forces in this game, the exchange. It's easy to rotate it, but it's immediately follows from this equation, right? M dot dm dt is 0, so the magnitude is conserved. All the dynamics is only angles, only precession, rotation. Okay, this is the most simple geometry, a plate, which is of course a limiting case of an ellipsoid. So we have here external magnetic field in the z direction. The sample is magnetized in the same direction. So the constant internal field, I call it now H naught, is also uniform in the z direction, and this is the relation between external field, internal field, and magnetization. So this demagnetizing tensor here is very simple, only one component, ZZ component. But well, we know this even from the other point of view. It's simply the boundary condition for magnetic induction. So magnetic field jumps, magnetic induction, its normal component is continuous. Okay, so this is the equilibrium situation. Now assume we excite the sample with external time-dependent magnetic field in plane, in the xy plane. Well, the internal small h field is the same as the external because the tangential component is continuous. So this h, the small h field exerts torque on the magnetic moment and causes precession. So this is the typical setup for a ferromagnetic resonance. And then these are the equation. So the magnetization, this is the Landau-Lifshitz equation for that simple geometry. H naught is the field inside, its constant part, and h small h is the time-dependent part. If we linearize this equation, writing magnetization as m naught plus some small corrections, we have a linear equation for this small m, and it is basically driven, it's very similar to an oscillator driven by the external force. In the absence of driving, we have eigen oscillations with the Larmor frequency, omega h equal gamma h naught. And this is the same story, but in what is called in-plane geometry. Here the external field and the magnetization is in plane, the constant part, and the exciting field, the time-dependent field is coming. It has now a normal component. So it's again, we can study precession, oscillations of the magnetic moment in this geometry, and the frequency, the natural frequency of oscillation, now it is different. That because the boundary condition now different. This small h now has a jump at its normal component has a jump, and the tangential component of the constant magnetic field in the z direction, it's continuous. So now the resonance frequency, the natural frequency of oscillation of this rotation of this magnetic moment is different. It's omega h times omega h plus omega m. So now there is an extra term. Well, I denote by omega m this gamma m0. So far I didn't mention dissipation, but there is of course dissipation in this story. So this is the Landau-Lifshitz equation in presence of a dissipate. That's how they introduce phenomenologically a dissipative term. So alpha is some constant, and this m cross h effective, you can think of it as some extra term in the effective field itself. So there is now an extra torque acting on magnetization, which drives alpha is positive. So this torque drives the magnetization towards equilibrium. And later, Gilbert introduced a dissipative term in a somewhat different form, m cross dm dt. You see that it is similar because if alpha is very small, then I can substitute for dm dt this first term. It becomes in the form of Landau-Lifshitz, but one can show that there is a mapping, that you can introduce new values for alpha and gamma in one equation to transform it to the others. So there are two forms of a dissipative term. This is Landau-Lifshitz, this is Gilbert.
How do I see that that's lost since the first term is not lost?
I'm sorry?
How do I see that that's dissipative?
The second one?
Either one.
Or either one. Okay, so there is I made here a little drawing. So you can see that these terms drives the magnetic moment towards, if I change the sign of alpha, which I will do in a moment, we'll have amplification. Okay, so I gave you a short introduction to Landau-Lifshitz equation. Now you know how magnetic moment behaves in a ferromagnetic layer. Next I will discuss two coupled ferromagnetic layers in a PT geometry. So in a PT configuration. So we heard in Carl's introductory talk various setups for PT symmetric structures. There are PT symmetric structures in optics, electronics. I can add acoustics, some recent work, PT symmetric acoustic structure, BEC. So PT. So there are many PT. Well, I hope the referee, our referee, is not in the audience, so I can use the PT jargon as much as I want.
You are recorded, it become public.
So the referee will see the record.
But the paper is already published, so it doesn't matter.
So I'm proud to add to this list of PT structures and yet another PT topic, which I'm discussing now, PT magnonics. Well, magnonics is a relatively new subject where they manipulate spin waves or magnons. Of course, magnons and spin waves, that's a very old subject. But these days they can fabricate various magnetic structures, like a sequence of magnetic layers or magnonic crystals. It's like photonic. There is this subject of photonics. Now there is fashionable subject of magnonics. Actually, we are not doing really magnonics because I will not discuss spin waves, or if you wish, I can call it spin waves in the limit when the wavelength is larger than the sample size. So it's basically a uniform. I can describe everything in terms of one uniform degree of freedom, magnetization. There is no space dependent in the equations I'm showing. Okay, so this is the structure I'll be discussing. Two coupled ferromagnetic layers, one with loss. This is with loss. The second is with gain. Gain meaning changing the sign of this alpha. And later I'll explain how it's perhaps possible to do experimentally. So these layers are separated by a thin spacer. The spacer can be either non-magnetic material or some other magnetic material. These are already details. If it's non-magnetic, then it should be really very thin because they will be coupled by exchange forces and by exchange exponential decays in space. But if it's a magnetic spacer, then it's different. It can be quite thick. So this is the coupling term. It's called ferromagnetic coupling. If the layers are left to themselves, then their magnetic moments would align, would be parallel.
Spacer is magnetic?
Yes, so that's what I was saying. It can be non-magnetic, but then it has to be really thin. But if it's magnetic, then it can be some other magnetic material.
Is there a role of magnetopustry and anisotropy?
Well, I will not discuss anisotropy, but generally in this Landau-Lifshitz equation you can introduce, and sometimes it's important to have an anisotropy. But if the spacer is magnetic, then you have dipolar magnetic forces. They are long range, so the spacer can be thick. If it's non-magnetic, it should be really thin.
You're going to explain why you need a spacer at all?
Because I want to have some weak, some coupling between, because if I have, if there is no spacer, then I don't know how to control this coupling. Then I will have some, just one magnetic.
So you want to have control over the coupling between the regions?
Yes.
Like a gauge structure in electronics. Gauge. Electronics.
Okay, so now these are the Landau-Lifshitz equation for this structure. There are, so we still have this usual torque term. There is now the coupling term and loss in the first and gain in the second layer. So they look very much similar what was shown already here for optics, for instance, and other fields, but now it's vectors. We have two vector degrees of freedom in a PT-symmetry configuration coupled to each other. Well, just by looking at those equations, you can see that they have a certain symmetry, what we call PT-symmetry, because if I switch, so first I switch the degrees of freedom. I replace, well, A stands for any of these, M1, H1, M2, H2. So I switch all one with 2. I switch the degrees of freedom in the layer. So I'm looking at the second equation. Then it becomes almost similar to the first, but not quite, because the sign of alpha is different. So I need another transformation. This is time reversal. So now I switch t to minus t, but also a to minus a, because this is time reversal symmetry for pseudo vectors. All these are pseudo vectors. So we have to switch to change time t to minus t, but also flip the directions of all the vectors, and then I see that the second equation is mapped on the first and vice versa. So this is the symmetry we have, and this ensures that the eigenvalues for this problem will be either real or come in complex conjugate pairs. So that would be study next. We linearize those Landau-Lifshitz equation and set h there is no h external because I want to study eigen oscillations. So these are now the two coupled equations in the linear approximation, M1 and M2. Well, omega h is still this gamma h naught, but instead of talking about coupling k, I translate it into frequency omega k. So omega k is the coupling in units of frequency. Okay. Well, this is a very stubborn slide. Tampikos can testify that yesterday night it was this M1 plus M2 was below, and it was M1 plus M2 equal small m, because I'm doing now I'm doing the change of variables. Instead of M1 and M2, I introduced the center of mass variable M1 plus M2, which I call now m, small m, and M1 minus M2, the relative. But for some reason, okay. So I don't see what happens, but okay. So this M1 plus M2 equal m, just a notation for the center of mass variable. So now the equations look really simple, because for alpha equals 0, the two eigenmodes get decoupled. So we have what we call the soft mode with eigenfrequency equal to omega h, and then M1 and M2 are parallel. So delta M is 0. So this is this oscillation which is easy to excite. And then there is a hard mode with kind of a gap. Omega 2 is now equal, its eigenfrequency is omega h plus twice omega k, where the magnetic moments oscillate out of phase. Well, pretty standard, the same as two coupled oscillators. Okay, so here I draw the evolution of these eigenfrequencies when alpha is switched on. So for alpha 0, these two eigenmodes, omega 1, omega 2, alpha increases, the frequencies changing, the imaginary part is still 0, no decay, no amplification, but and this is the exceptional point. So we saw this kind of drawings in many other examples. And for alpha larger, some critical value, there is bifurcation, and we have two modes, with one with decay, the other with amplification. The parameters here, the coupling omega k is 0.54 in units of omega h. The values of critical frequency is written here, and the critical value of alpha is turns out to be equal to this combination of omega k and yes, Yes, you can write it as omega k over omega c. Well, there are superscripts and subscripts here, but basically it's very simple. Here we study the eigenmode. It's the structure of the eigenmode. So the superscript n refers to the number of the mode. There are two modes. And this one, the subscript 1, 2, refers to layers. So we're asking how this mode is distributed between the layers. So in the PT exact phase, the ratio of m, we took y component, but one can take x component, the same thing. The magnitude of the ratio of the two components, I mean, in layer 1 and layer 2 is 1. So the mode is equally distributed between two layers. But in the broken phase, one mode predominantly goes into the first layer and the second mode into the second layer. Well, now comes dynamics. So here, dynamics, it's more convenient to discuss in terms of the angles, right? Because the magnitude of the magnetization is conserved. So it's enough to speak about angles. So this is in the exact phase, in the PT exact phase. We compare the linear approximation with the numerically exact solution of the whole nonlinear problem, and they are practically coincide in this region in the unbroken phase for the parameter that we use. So we take some initial condition in this example, theta 1. So the magnetization in first layer was in equilibrium and the second layer was displaced. And then the layer talk to each other, and this is the dynamics. So both theta 1 and theta 2, the polar angles change periodically, and the linear approximation is very good. Well, there is also post dynamics in the phi in this azimuthal angle, but that's just some quick rotations that we are not showing here. But in the broken phase, of course, nonlinearity is crucial, because in the linear approximation, in the broken phase, there is a runaway. The system is unstable. So this is this black line, so it has no meaning when theta becomes large. But if nonlinearity is taken care of, and this we did numerically, then nonlinearity stabilizes this instability in the broken phase. So it's kind of a limit cycle. So we have some oscillations. The other possibility would be that the system is driven to a fixed point where the two moments become anti-parallel to z direction that I will show in the other geometry. Okay, and this is dynamics at the critical point. So again, it's in the linear approximation, it would be linear growth of theta, but with nonlinearity, it's kind of oscillations. This is the other geometry, the in-plane geometry. Here, the field and the equilibrium magnetization is in plane. This is z direction. So the equation is a bit different. There is an extra term in those equations, but qualitatively it's the same story. So I will really skip this. It's very similar to what I showed before. This is exact phase, linear approximation. This is the broken phase, and here the parameters are such that the system, that nonlinearity drives the system to a fixed point where the angle both angles, theta 1 and theta 2, are in the negative z direction, because this is the stable fixed point. Okay, so now I will briefly discuss the two possibilities how to introduce gain. So far I just told you that I switched the sign of alpha. So one way to introduce a gain is via parametric driving. I will remind you what is this parametric driving. Sorry. Well, I told you that I developed Parkinson when I touched this laser pointer. Okay, so you probably know from your mechanic course that.
Before you proceed,
Yes.
if the thickness of two layers was different,
What
Thickness is different.
thickness? Yes.
L1, L2,
Yes. Well, we want to have maybe this thickness, then you can compensate it with some other parameter. But we want to have a PT-symmetric structure. So for alpha 0, we want really both magnetization are M0 are the same, H0 is the same. So and it's the same material.
but even for different thicknesses, you could maintain PT-symmetry by wearing something else.
Well, maybe, yeah, but we have to look at this.
That's not so easy.
So it's the same equation as with oscillators. So you start with two identical oscillators, and then you introduce gain into one. And if they are not identical, the masses are different, probably you can compensate it by lengths of the spring, I don't know, because the important thing that they have the same eigen-frequencies. Okay, so this is the parametric driving of a harmonic oscillator. So this is the equation. It's you change the frequency of the oscillator by adding some small harmonic term. So this is the parametric driving. You can think of, you just pull this string so it becomes shorter or longer. This is the parametric driving. Standard problem. And the result is that, so you have oscillations, but the envelope grows exponentially, and it's limited by nonlinearity. So this is what I would call mimicking gain in a mechanical oscillator. It's different than what Carl was telling us at the beginning, that you can mimic gain by kicking oscillator, but this is different. Kicking or periodically driving the oscillator, this I wouldn't call an instability, because you saturate, the amplitude gets saturated, even in the linear approximation. But this is really an instability. So, well, there is a solution x equals 0 to this equation, but it's unstable. At the moment when you have any initial, even slight deviation, you have exponential growth. So this is mimicking gain in a mechanical oscillator. And the same idea we can use for our system. So I'm taking now the magnetic field is now has a constant part as before, and this time-dependent part with frequency, which is twice the natural oscillation frequency, and this is only possible to do, we noticed, in this in-plane geometry. And in the in-plane geometry, well, we end up with these two equations, and we can study them, but at least to make the point, I can see that for omega m is gamma m0, remember, and omega h is gamma h0. In this case, I really have, well, I eliminated my in favor of mx, I really have the same equation for mx as I showed for a parametric driving of an oscillator. So that's one possibility to introduce gain into a ferromagnetic layer. The other possibility is called spin transfer torque. That's a well-known notion in spintronics. You know, it goes back to, they got Nobel Prize, I think, for this kind of things. But also Nobel Prize, Fert and some French, for giant magnetic resistance. Giant magnetic resistance. You know how polarized spin currents react to magnetic layers. So to understand a bit of this, we have to use this notion of spin density. So it's like charge density, particle density, but now it's a vector. Spin density is a vector. Okay, so this is something standard, right? Psi is a spinor, but its component can be space dependent. So it's like the three components of the expectation value of a spin, right? In real space. So this is the spin density, and spin current density is also, it's, if you ignore sigma, then it's like, you know, defining a current, charge current, but sigma is crucial here. Spin current density is a tensor because it has two components. One component is space. It shows where the current flows, and the other is spin. Well, I'm giving here an example. Take a spinor, which is just, you know, a particle moving in x direction, but its spin state is this spinor, A up plus B down. Plug it in here, you will see that there are three non-zero components of this spin current. The first component shows that the particle is going in the x direction, and the second component shows you the expectation value of the spin in the three directions. Okay, so here I'm taking, so this is an example again of spin torque. This is the spinor. I have a stream, a beam of spin polarized particles. They hit a magnetic layer. There is a transmitted and reflected wave. Well, probably here that should be minus IKX. Should I blame the laptop, or it's my fault? Okay. So there is a transmitted flux and reflected flux of particles with spin. And the point is that the reflection and transmission coefficient depend on the state of the spin. So for spin up, we have R up, reflection amplitude up, transmission up. For spin down, it's different. Well, you can think of an extreme example when spin up is fully transmitted and spin down is fully reflected. So it will simplify. So you see immediately that the Z component of spin must be conserved in the scattering process, the Z component. But X and Y component are not conserved. But it means that this stream of particle, it exerts torque on this magnetic moment. Okay, so and this torque can be written as product of this magnetization cross S cross M. S is the direction of spin polarization. For instance, if S is parallel to M, no torque. because and the torque will rotate this magnetic moment when up to the point that it will be parallel to this S. When S is parallel to M, then there is no torque. Okay, so this looks as another way to introduce gain, because you can have a torque which deflects the moment, this magnetic moment from its equilibrium position. So that's basically the end of my talk. I introduce this notion of magnetic gain and loss. Told you about how to realize magnetic gain in a ferromagnetic layer. So we discussed some new type of magnetic steady state and also dynamics. Well, we are in contact with the experimental group of Vale Vardeni in University of Utah. So they fabricated such two coupled layers with a spacer, layers which talk to each other, but they cannot introduce gain.
How do they measure the magnetization with external sensors?
Well, what you measure, how do they know, for instance, the coupling? Because they measure even without gain or loss, if we forget it for the moment, they simply measure the eigen-frequencies of the two modes. If the layers are decoupled, then they are identical. They are degenerate.
By microwave?
Yes, they measure it by ferromagnetic resonance technique. So they are sending microwave, and when the frequency of the microwave hits the eigen-frequency of the structure, you have absorption, large absorption, peak, and the absorption. So they can detect two different splitting of these two modes. But again, it's probably a more complicated business. And of course, then there are always experimentalists always asking you questions, but what we can do with it, how useful is this? So to this, I can only answer, ask not what PT-symmetry can do.
Sounds like 1963.
Are you a Berliner cookie?
Yeah. Thank you very much.
Yes, thank you for this.
So
lovely
I can disconnect myself.
Yes, you can disconnect yourself. So thank you for your lovely clear talk. Are there any questions? Yes or no?